TimeGPT, a generative pre-trained model, right, for time series forecasting. So essentially, take what ChatGPT does for language and TimeGPT does it for time series forecast. I had the chance to test it. It got scary because it actually worked better than my model. For a particular situation, okay, so it actually worked better. So it made better forecasts. In another situation, so what I've noticed is that as you go for more long-term forecasting, you're actually reaching some of its limits, and then the predictions actually start to deteriorate pretty fast.
Tell me about your work in time series. What is time series forecasting and how are we using it to predict the future?
All right. So first of all, I have to say I'm entirely self-taught. Okay. So my all my work on time series is from me learning it on my own, reading a bunch of articles, a bunch of books, taking courses, and then so actually the story is uh, a lot of the stuff at the time I was learning was actually in R. Okay. I have nothing against R. It's just I can't code in R. Okay. Like for the life of me, I can't code in R. I'm a Python developer. Okay, so the main challenge at the time was translating all this R code into Python. Okay, which I guess really helped me understand and master the subject. And so that's why I ended up, developing resources, so articles and courses on time series forecasting using Python. So that's really like my main motivation behind that. Also, my career right now is at a big financial institution in Canada. So of course, time series present in everywhere, right? Anything related to time. And so to go back to your question about what are time series exactly, right? So it's basically any data point ordered in time. Um, and the keyword here, right? The important part is ordered in time. So a time series, it has an order. Okay, so whatever happens on Monday has to come after Sunday and before Tuesday, right? And that's super important. So I would say I started my career with more like traditional machine learning projects and stuff like that. And in a traditional regression problem, right? Suppose you're trying to predict the prices of houses, right? That order doesn't matter in a sense, right? As long as you have features like the number of bedrooms, the size of your house, number of bathrooms, etc., you're shuffling your data, it actually benefits the model. With time series forecasting, you cannot do that, right? You cannot tell your model, you can't shuffle the data of your model, right? Your model can only know what happens in the past in order to predict the future. So that's also a little bit different. And so other techniques are applied in those kinds of problems. So that's what makes time series a bit special to work with.
You said financial modeling that can kind of be used in financial services. So tell me a bit about how these kinds of modeling techniques are used. Like, are they the only kind of tools that we have when I think about the word prediction? Is it am I going straight to time series, or is it the only thing you can do? Are there other ways to do things too?
No, so there's a bunch of stuff that you can do with time series, right? Essentially, it's regression, classification, and anomaly detection. So anomaly detection, right? Suppose I don't know, you're monitoring your servers. Okay, suppose you're AWS, right? You're monitoring your servers. At some point, you can have an anomaly, servers goes down, or you have like an uptick in activity, something like that. So, you can do anomaly detection to see if there's a problem, there's a change in activity. Time series classification, I think, is not talked enough, but the use cases are amazing, especially for speech recognition. So when you think about it, right, basically like saying words, vowels, etc., like the way they model this is like it's sound waves over time, okay, or like pitch of your voice over time, right? And so they're actually using that to classify who is speaking or what words are you saying. So I'm not entirely sure if it's time series classification behind that kind of technology, but it is one of the applications that exists. And of course, you can have like is it a healthy ECG monitoring, right? Like, is it a healthy heart or not? Stuff like that. Okay, so bunch of stuff that you can do with classification and time series. And then you have the traditional regression, which, like you said, predicting the future, right? So are the interest rates going up or down? Is the temperature going up or down? Whatever, right?
It's interesting that it's not just say predicting the future, but also you can kind of use the same sort of like patterns as they do speech, right? So
Yeah,
there's this kind of huge variety. So I
yeah.
mean, one thing I'm struck about is how maybe it's not just been in the past, but definitely like in the last few decades, it's
Hmm.
getting so much better. Like in looking some of the graphs or some of the predictions that things can do, or just people
Yes.
can note like how good translation and so many things are, and
Yeah.
like. Is it surprising to you how good things have become, and like how recently has it become like that, and why can these kind of techniques be so good at predicting?
It's not. I mean, the surprising part is how fast we managed to get access to compute power, right? And have those efficient ways of computing stuff. Okay, so that basically, that basically goes back to what they call the AI winter, where at some point the models theoretically existed, but they simply didn't have the compute power to apply them, right? And then at some point the compute power caught up, and that's when, all of a sudden we can train machine learning models on our laptops and have like machine learning models on our phones and stuff like that. And all the way to now where we're building, those very large language models, like billions of parameters, and it's all of a sudden doable, right?
Well,
So
what do you mean by compute power? What changed and why?
So it's really, having access to those GPUs, having access to parallel computing. Now we actually have basically the hardware to compute all that data, and also, the technical abilities and storage to store data, gather data, analyze that data. This is really what makes all those models super powerful now and really possible. So that's why the entire field is booming right now, not just time series forecasting. So that's why in a sense it's not really surprising, right? So of course now we can correlate a bunch of stuff with our time series, and we actually have the compute power to put this in a model and have a regression being done. But that really comes from the entire hardware being able to follow now all the theoretical work that was done before, but they still couldn't apply it at that time.
It's very interesting that it's actually kind of on the hardware side
Yeah.
that the improvements came,
Yeah.
so I mean, for example, because of course the computational abilities is not just in, well, very related is kind of things like chat GPT, right, which is predicting, you could say, words,
Yeah.
right? And so would you say that even those technologies were kind of many of the things, the interesting technological developments like in the code were already, a lot of them were there waiting, but we just needed to have ways to actually be able to put training data and computational power into them? Or what kind of developments have there been on the software
Um,
side to?
Yeah, so time series is, it's a special field, I would say, because for a long time statistical modeling dominated. Okay, so I mean, if you know a little bit about time series forecasting, right? The traditional statistical models like ARIMA, exponential smoothing, BATS and TBATS, stuff like that. So those were really the models that worked, and they still work. They work very well, right? But it's very the traditional statistical modeling where you have to know a lot of information about your time series to apply them. Okay, so you need to
Right.
know about your seasonality, the type of trend, etc., and that's how you apply those models, and those models will work. And so for a long time, and until very recently, they're still like they work. Okay, they work really well. But then machine learning started to catch up. Okay, then we started. Okay, let's try decision trees. Let's try XGBoost. For regression. And then in recent competitions, so those big, there's like a big forecasting competition called the M3, M4, etc. Uh, that's when, at some point, machine learning models were destroying statistical models. Okay, so like they were very performant. Okay, so models like XGBoost, for example. And that's when they're like, okay, now machine learning maybe is better than statistical models for regression. And then all this work on deep learning, so we started seeing deep learning. Oh, deep learning works really well with computer vision. Deep learning works really well with NLP. Let's try deep learning on time series as well, right? And that's when we saw, oh, now we can model time series with deep learning too. And of course, access to the compute power, right? Deep learning, bigger models, a little bit, requires a lot of data, right? That's when we managed to leverage that kind of data. And so now, yes, deep learning is getting very, very good at time series forecasting. Personally, I think it is better in some situations, right? Not every situation. So, unless you have like, I don't know, thousands of data points, don't do deep learning on your time series, right? If you have like 1 year of data, I mean, your statistical model is going to work really well. But yeah, that's the kind of
Go for
shift that happened.
it. Yeah, it's if I get the story correctly, would you say that kind of in the past we had these kind of, as you say, ARIMA, these statistical models where we needed to go, okay, let's manually really understand
Yeah.
the way that we the thing we're studying, right, the forecast, and then
Yeah.
once we really understand the structure of it, we can put a model together bit by bit and
Yeah.
then do it. And we thought that was the way of going, and that
Yeah.
machine, but then we kind of had machine learning and all these fancy cool things there, and we're like, oh
Yeah.
wait, is this going to be better? Is time series done for? But then are you kind of saying that now actually there's kind of been a mix where we can use time series, but we can also use the benefits of kind of machine learning.
Exactly. And it's also important to understand, I think there's a difference between statistical modeling and machine learning. Okay, so with statistical modeling, it's more like input the right parameters in your model to fit your data and model your data correctly, right? Which is why, when you're doing exponential smoothing, for example, you need to specify, do you have a seasonality? What is the kind of trend? Is it increasing or decreasing? Is it an exponential or a linear trend? And if you have a seasonality, right, what is your period of your seasonality? So is it like daily, weekly, yearly, whatever? So those are important parameters to input into your model so that you have a good model. With machine learning, you kind of abstract that part, right? It's more like, here's your data, here's the prediction you have to make. Now find a way to map, right, the past to the future, in the most efficient way possible, right? Minimizing some kind of metric. Okay. So that's really like the big difference essentially. And so of course it abstracts some stuff. But I would say like the domain expertise, right? So even those advanced deep learning methods, they still bring some kind of like time series elements in it. Like it's still, yes, it's neural networks, but we're trying to capture seasonality. We're trying to capture trend, but it's just like more complex relationships in seasonality and in trends that those models can capture. Whereas, with statistical models, you're a bit more limited, right? Like I said, it's a linear or exponential trend, but your series, right? What if your trend shifts at some point? What if it's not entirely linear, not entirely exponential, right? So that's where like the limit really is reached with statistical models. Whereas with machine learning models, you can train those parameters and adapt to non-linearities, etc.
I see. So you can kind of get to more model and understand and predict more complex kind of
Exactly.
series
Yeah.
and patterns.
Yeah.
I mean, it's interesting that you can kind of like in the past couple of years they've been able to become though better at predicting say more complex patterns, but also more general. So
Yeah.
could you speak to like the kind of advances in what kinds of things have been like, able to be modeled and predicted?
Well, so let's see. I mean, usually in academia, right, in the papers, there's this, I would say, group of data sets that are used all the time as benchmarks. So we have it's what they call the electricity load data set. So you have pretty much 7 series, 6 features, and a target series, and just trying to predict the temperature on the electricity transformer. You have another one, it's called the weather data set. So you have like a bunch of features. So it's weather, temperature, humidity, wind speed, etc. So again, a bunch of features to predict weather. And you also have traffic. I've never really worked with the traffic data set, but I think it's something about like car volumes, and then you also have like a bunch of features to it. So yes, as years have passed, right, we have become better and better at forecasting those data sets. Pretty much what I remember is that the first model really, setting the state of the art in that field was called NBeats. So, pretty much like NBeats, by the way, stands for Neural Basis Time Series Forecasting. Neural Basis Expansion, Time Series Forecasting. And, an entire deep learning architecture to forecast time series on a long horizon. Long horizon, of course, is a is a harder challenge, right? Because as you predict further in time, the chances of making mistakes get higher, right? Your uncertainty is higher. So long horizons usually stands at a minimum of 96 time steps into the future, all the way like to 720. So that's what usually they test in academia. And so NBeats, set like really the pace, I would say. And then, it just went up from there, then it was like NHITS, which is like a hierarchical way of forecasting. So it's like, what if I can model the monthly, for example, relationships, and then the daily, and then the yearly, and then hierarchically, aggregate those forecasts. So that was better than NBeats. And then we moved on to like Patch TST, which applies to transformer. And honestly, in my opinion, this is the only successful implementation of the transformer architecture for time series forecasting. So if you want to talk more about, applying transformers, I'm all down for it. But to me, that's the only successful implementation. So that really pushed the state of the art a little bit more, all the way to super recently with TS Mixer. So a model released by Google, like this year, so like very state of the art. And this is like it's interesting because it's only like a multi-layer perceptron model. Okay, so it's essentially like a very simple architecture, but they're doing what they call feature mixing. So basically they're transposing the matrix, in a bunch of directions and running it through the MLPs. And that again, outperformed the models out there. So yeah, we're just getting better and better at forecasting those. And it's also a matter of like, yes, finding those new architectures, leveraging also exogenous variables. So, external variables, right? So like, take for example, the weather data set, right? Like how can I use the information from wind and humidity to actually forecast my temperature? So we're just getting better and better at using that information to inform our predictions, essentially.
Right. So like at that last point, not just using a forecast on like one specific thing, but let's get other data points from other places, and actually that can help improve it. I mean, it's interesting that you say like 90 and above, time periods. Like, can you put that into context? Is it like if you have like yearly, like if you have like I don't know, daily data, is that like you can predict a year out? How far ahead can we do that? And then like how bad do the predictions get? How quickly, or how can we think about how well we can predict things?
That's a very good question, and I think every forecasting project has to start with that question, right? Like, how long do I want to predict for, and is it reasonable as well, right? So, for example, suppose that you only have yearly data, okay? So you have one data point per year, okay? Like, does it make sense to forecast 72 years into the future? Maybe not, right? Like, it doesn't make sense. The frequency of your data simply doesn't make sense, right? However, the data sets I was telling you, like the electricity transformer data set, for example, you have data every 15 minutes. So if you're forecasting 96 time steps into the future, well, you're forecasting 96 times, steps of 15 minutes. So that's like, wait, what is that? 96 divided by 4, that's 24 hours, right? So you're actually forecasting a day into the future, right? But at 15-minute time steps. So that could make more sense, right? Simply because you have the frequency of your data there. So it really depends on the objective, right? And also the kind of uncertainty you're willing to take, okay? So I've had, projects and businesses where they tell you, oh, we want to forecast for the entire year every day, right? Well, does it really make sense, to forecast like a full 365 days into the future? Like, we're going to get very uncertain after 30 days, most probably, right? Like the predictions might degrade or something might happen, right? So it's, it really depends on the frequency of your data, essentially. And also like, what is the objective? What is the goal, the business goal behind it, essentially?
I mean, do you, on that point, do you have any sense on like how far ahead like economic predictors, people, central banks are going to be doing like interest rates, and we're going to have, macroeconomists telling us like how the economy is doing and things like this? Like how far ahead can they do it, like realistically? Do you have any sense on that?
My understanding is like interest rates, they vary monthly, right? So it's not varying every week or something, right? It's pretty much set for the month. So, to me, something reasonable would be probably 12 months into the future. Um, but again, it's really like how uncertain are you willing to be, right? Because of course, any prediction has some kind of uncertainty, right? You can calculate those with like prediction intervals. And so at some point, it's just like in the future, your prediction interval is going to be very, very large. And so you might still be right in your prediction interval, right? So like, I don't know, suppose your interest rate right now is at 3, okay? And you predict that in 12 months, it's going to be between like 7 and 1, okay? And it ends up being at 6, okay? You're still right, kind of, but your range was so high, right? It was so large. So it really depends. Like, is it useful information to you if I tell you, right, in a year, the interest rate is going to be between 1 and 8, Like, is it useful? Maybe not. However, I can tell you that, for the next month or the next 2 months, it's going to be between 5 and 6 or, 3 and 4. And that, okay, that's more useful information. So it really depends. There's no real mathematical answer, or at least I don't know it. But again, it really depends on the objective and how uncertain you're willing to be, essentially.
Tell me about the different kinds of models that, because it's interesting that you say that there are improvements going on, but they're not necessarily using the same architecture.
Yes.
So would you be able to speak about and explain like some interesting developments? And of course, as you're saying, like people are like integrating machine learning into
Yep.
these kind of forecasting techniques. So maybe speak about that too.
Yeah, sure, for sure. So let's see. First of all, you can virtually apply any model for time series forecast. Okay. So I mean, if we're focusing a little bit more on the machine learning side, right? You can apply any regression model could technically work. Okay. So you can do decision trees. You can do linear regression. Let's not consider this a machine learning model. But anyway, decision trees, you can use them. They actually work pretty well, right? On the deep learning side, you can have the multi-layer perceptron, so your basic, neural network. That works really well. You can have convolutional neural networks. I know it doesn't make much sense. I mean, at first when I saw those, it didn't really make a lot of sense to me because CNNs, they're very popular for computer vision, right? So their ability to analyze some kind of a 2D matrix and then, treat images, that's where CNNs have mostly performed. But you can also apply them to time series. You can use them in conjunction with LSTMs, so long short-term memory networks. They work really well together. So virtually you can apply anything for time series forecasting. However, what has been shown to work really well, again, from the academia and everything, MLPs, they work really well. Okay, so you're just your traditional neural network. Okay, of course, it varies in how you put them together and how you're basically analyzing your data beforehand, right? But MLPs as a base architecture works really well. So again, NBeats, NHITs, TS Mixer, all those MLPs work really well.
So what would be like a traditional neural network? You're saying that these can be applied to like time series forecasting, but what kind of does that look like? Not in, I don't know how much detail to go into, but
Yeah.
give us an idea of what that means.
Yeah, sure. So I mean, so again, if you know a little bit about deep learning, right? The MLP, when I say it's the traditional architecture, it's like really you have your input layer, and then you have like your fully connected forward layers, right? And then you're gonna have your activation function, so usually ReLU, so the rectified linear unit, and then you can add a bit more techniques to how can I say, improve the efficiency of your network. So maybe you can add some dropout, you can add some normalization before training your model. You can add a residual connection as well so that you can train deeper models, but still keep the computation efficient, right? So that's essentially what is happening in those kind of models, right? But it's really fully connected layers. You're going to have some dropouts, you're going to have some residual connections here and there, but it's just like a bunch of layers, one after the other. You stack them, and it works. It works
Right,
really well.
Right, and you put inputs in. There's many different, there can be weights and activation functions in between, but then you're getting something out, and
Yep.
and I guess there's training procedures. Okay, that's helping me understand it. So that's
Yeah.
kind of a traditional neural network, right? And you were
Exactly.
saying that like these kind of in some of the more recent developments sort of in the literature, these have been kind of used?
Yeah, exactly. So those they're still. I mean, it's funny because they're not part of the most recent literature, right? The most recent literature is actually focusing a lot on transformers, okay? And of course, that comes from NLP, right? So there's this parallel between NLP and time series that people are doing, and intuitively it makes sense, right? So we said earlier, a time series has an order, right? Whatever comes on Monday is after Sunday and before Monday. And it's a lot like speech, right? It's a lot like the language we speak, right? So the order of words matter, right? And depending on where the word is in your sentence, it can have also a different meaning, right? So for example, take the word bank, okay? So you have bank, the financial institution, or you have bank like a river's bank, right? The side of a river, okay? And so depending on which word precedes or is after bank, you're gonna know what it means. And so we know very recently transformers, they were, I don't want to say like transformative, but like they changed a lot in the
Yeah.
field of NLP, right?
So tell me
So
about them.
like,
How did they change natural language processing, and what are they doing? Like, I guess am I right in saying they're like used in ChatGPT and these more
yes,
recent large language models?
yeah, absolutely. So and the crazy thing is that the transformer architecture is from 2017, which might not seem that old to like general people, but in the field of machine learning, something from 2017 is like outdated, right? Usually
Right.
the state of the art lasts for 2 to 3 years max. Uh, but the transformer architecture from 2017 is still used. And like you said, it is behind ChatGPT. Okay, so all those new generative models, they use the transformer architecture, right? And so of course they have been shown, like it's proven, right? They work really well for NLP. Okay, like it's
Yeah.
almost like we're almost done solving the idea of constructing sentences, right? Like the sentences that ChatGPT generates are amazing. They're very well constructed. Like not talking about if they're true all the time.
At this point, our recording failed when we were talking about how transformers and attention work in ChatGPT and these kinds of architectures. So the next section is just going to be me coming back and reiterating how attention works, and then Marco explaining how attention works in ChatGPT. Okay, hi Marco. So we were talking about attention in
Yes.
transformers and how ChatGPT was working. So talk about this, keep going about how with this attention mechanism you can effectively, with words, you're not just like in some sort of normal neural network, you put everything in and then like you
Yeah.
get one thing that comes out. You're like, actually, this word actually it's related to a word a couple words back.
Exactly.
The it is referring to the chair that was being referred
Right.
to. So you
Yeah.
get this kind of more dynamic system. Could you keep explaining that?
Yeah, so I mean, you're pretty much describing it really well.
Okay.
It's
Thank
essentially
you.
what the attention mechanism is doing, right? So, but the interesting thing is that we're letting the computer find those relationships, right? So we're letting the computer find relationships, and like you said, okay, this adjective is related to this noun, or like this pronoun is related to this, etc., right? So that's what happens in the encoder part, okay? And then it goes into the decoder, and the decoder basically is going to get the information from the encoder. And then when you input some new information, it's going to, knowing what it learned from the encoder and knowing this input, generate some new output, right? And so that's basically what is powering all those generative solutions that we see now. So, ChatGPT, for example, the most popular. So that's why, when I input a prompt, right, or a message, write me a joke, it is able to generate, a sentence that should be a joke, right? And so yeah, so there is this, again, this aspect of sequence, right? So I'm learning, about sequences of data, sequences of words to output a sequence of words. So researchers try to implement that for time series, right? And it makes sense intuitively. It makes sense, right? I have a sequence of numbers, whatever events that happen over time. Let's learn about relationships between those events, so that when I input a new event, or now that I know this relationship, output a sequence of values in time. But the truth is, they never really worked that well. Okay, I find it interesting. Okay, I find it very fascinating, right? So they tried transformer, temporal fusion transformer, and then there was like a bunch of work, informer, autoformer, etc. Like all of them trying to apply the transformer architecture, and then uh, like this is a bit of criticism, okay? But
Mhm.
they were all claiming state of the art results, right? But they were always comparing to other transformer architectures. But when you compare transformer architectures to MLPs, the MLPs are better, right? So,
Right.
that happens in academia. It's okay, right? They're saying, oh, we made a better transformer. We made a better transformer for time series. But the truth is, your transformer is still worse than like the MLP solutions, right? And there was also a paper, I think in 2022, and it was funny in the sense that it says most linear models, like take a linear deep learning model, works better than your complicated transformer. Okay,
Right.
and it's important to know, right? Because the transformer it's big, it's complicated, it's long to train, right? Like it takes a lot of computer power to train your transformer, whereas an NLP that's super fast. You don't even need a GPU for that, right? Train everything on the processor. It's going to be super fast and it's going to generate better results for your forecasting task. So
Right.
that's a bit what happened essentially.
Yeah, and if I understand the story correctly, so we in 2017 or maybe around that we developed transformers, which
Yep.
they're really useful for like say natural language processing, ChatGPT and things are using them right now. But
Yep.
actually, it turned out that that's like no matter how cool they were, we just couldn't really apply them to time series forecasting and predicting, and people would make models with them, but like even simpler models just they kind of wouldn't work as well, and
Exactly.
right, and
Exactly.
is
Yeah.
that and
Which is why I say that patch TST is the only, I believe, successful implementation of transformer, because that was shown to not only outperform all the transformer architectures that we see, but also outperform the MLPs, right? It actually delivered state of the art results. And by the way, patch TST, how does it how does it achieve those state of the art results? So the key is in patch, right? So it actually feeds the data in patches so that you can actually now have information on groups of time series sequences. And that's how basically that was I guess the key to unlocking better performances using transformer on time series forecasting. But still keep in mind, patch TST is very hard to like, not that it's hard to train, but it takes a lot of power, it takes a lot of computing resources to train. And then you have to see, is my I don't know, maybe 1% better prediction worth spending a lot more on computation than my MLP that is much faster? Maybe the prediction is going to be a bit worse. It depends on the situation, right? There's no state of the art for every problem in the world. Okay. But that element comes to mind when we're using those models.
I mean, when to understand that like patch model, is it so it's like zooming in on like small sections and isolating them and studying them separately, and that
Yes.
overall gets so that then does help get better predictions, but like that's also a lot more effort to be going in and splitting up the data like that, and
Yeah.
so it's
Well, it turns out it's actually a bit more efficient. So instead actually of feeding, one token at a time, one data point at a time, because you're feeding patches, you're actually going through the network less times, right? So, if you have 100 data points, so instead of going 100 times through the network, suppose you do patches of 5, then you're going through the network 20 times. But still, the just transformer in general, the attention mechanism and all of that takes a lot of time to train. Especially, if you want to reach those state of the art results, right? You're gonna have to train for a long time.
tell me about time GPT and the recent developments there.
Yes, TimeGPT. So, TimeGPT came out October 2023. That's when the paper was published. And really great team behind TimeGPT. So it's Nixlab that is behind them. They're really great. So I've used their libraries. I believe they're making one of the best forecasting libraries, open source forecasting libraries out there. Really, implementing ready to use state of the art models. They're great. I've met with them. They're like amazing team. And they came out with TimeGPT. So TimeGPT, a generative pre-trained model, right, for time series forecasting. So essentially, take what ChatGPT does for language, and TimeGPT does it for time series forecasting, right? And that's a huge shift in paradigm for the field. Okay, like we are used to fit our model on past data to forecast the future, and our model works only for that specific time series, right? Makes sense. And what they're saying now is that no, you can pre-train this model on a bunch of data, right? So on a, like, if I remember well, like 3 billion data points, different data sets. Okay, so like economics, financial data, weather, traveling data, like a bunch of different fields, right? So they trained on all of that. It's the transformer architecture, right? So it's still the encoder and decoder structure that we see to generate the prediction. But it's adapted for time series forecasting. And so in their paper, again, they claim state-of-the-art results. Okay, so compared to other methods. So and here they compare to transformer methods and also to some MLP architectures. So it's huge. I would say it's not available to everyone yet. Okay, so right now it's in closed beta. I had the chance to test it. And it got scary because it actually worked better than my model. For a particular situation, okay, so it actually worked better. So it made better forecasts. In another situation, so what I've noticed is that as you go for more long-term forecasting, you're actually reaching some of its limits, and then the predictions actually start to deteriorate pretty fast. So for long-term forecasting, models like NHITS and stuff like that still work better than TimeGPT. But for, short to medium term, it actually worked really well. And keep in mind that the idea is the model is pre-trained, right? So all you have to do is send your data through an API, you make an API call, and like in a few seconds, I mean, in less than a second, right? You're getting predictions back. And it also abstracts all this need or like expertise, that you need for time series forecasting, right? So yeah, it's interesting. I'm not sure it's going to remove the need, for professional forecasters and, having this domain expertise, right? But it is interesting as a solution, for people who just need, maybe they don't have the means to have a data scientist or just need some quick forecasting, I think it's going to be pretty cool for them. Yep.
Yeah, it's fascinating that like previously you might only use one specific data set, but now we can actually combine lots of different data input points and then predict many different kinds of series. And
Yep.
I mean, it's strange. You'd think that like individual models would be better individually, and maybe they still are. But like,
Yep.
what are the problems with trying to predict multiple different series with one model?
Well, again, like I really believe there's no one solution to all problems, right? So to me, I still see TimeGPT as another way of solving a problem. Okay, and so I mean, for sure, the model can only know what it trained on, right? And the idea of those very large models, right, is that you've trained it on so many things that it is likely going to, in a way, recognize what is happening and make some reasonable predictions. Okay, so that was the idea behind the 3 billion data points on data sets from various industries and domains, right? That's the idea. So yeah, but I mean, for sure, if you bring it, something totally unexpected, right? It has never seen before. Well, chances are it's gonna fail, right? And that's okay. That's expected, right?
Right. So it's still not designed to, take in data about basketball and baseball and football and then give you, cricket. Or would it? Is it possible that it could also maybe predict another sport based on
Well,
predictions of others?
yes, maybe it could, right? But again, it's like I said, we always have to test it against something else, right? And that's really important. So for anyone, I myself, I'm a data scientist. So anyone doing forecasting, doing data science, it's important to keep that rigor in our work. We're we're scientists, right? Like we're always analyzing performance against something else. And so never take something at face value, right? So sure, test out TimeGPT, but test it against something else, right? Test it against your own custom model that you're inputting, your historical data, and then you have your exogenous variables and whatever, and see, is it actually performing better or not? And that's when, base your decision on that, essentially.
Right. I mean, I'm interested in that point of the science of data science.
Yeah.
How can What are the aims of data science, and like how can we think about causality and trying to answer questions using data science? For example, from a scientific viewpoint, I'm an economist.
Yeah.
How should we treat, say, time series models when we're trying to think about, understanding why questions and why something causes another thing?
Yes. Very, very good question. Very good question. So let's see. First of all, to me, data science, you're answering some kind of a business problem using data. That's the way I see it, using some scientific approach. Okay. The scientific approach, again, is you're going to do experiments, you're going to test out different models, different approaches, right? You're going to have some kind of a measure of performance, of quality, right? So in the case of forecasting, is how far are you from the value you were trying to predict, right? And that's how you can say, okay, this is the best forecasting model. Now you touched upon something that is very interesting. I haven't spent a lot of time on it, but you talked about causality, right? Like, is this event causing this in my time series, right? The best method that I know of is a statistical test. So it's called Granger causality, right? And basically, this statistical test is going to tell you, is this series, when it varies, does it cause a variation in my other series, right? So there are ways to see, are my events, are my series correlated with one another and actually causing each other, right? This is beyond correlation, right? This is really like causing one another. So the tools exist, right? And it's a matter of, I guess, spending the time doing that test, and also having this curiosity of, well, is this impacting my series, right? Or using your domain knowledge again to understand, well, this is likely impacting my series. Let's verify this scientifically, right? Let's actually put a number on this, right? So
Yeah,
essentially how I see it.
it's helpful that you talk, like, distinguish between forecasting, predicting versus, say, Granger causality, or like trying to answer the scientific questions of why, and specifically if something causes another thing is different from specifically forecasting and trying to solve a problem. But even in trying to solve a problem, you can still try and approach it scientifically and think, like, we need to evaluate and have good ways of evaluating different models, right? And but in doing that, you can solve a range of different problems, right? And I'm interested then in the future of forecasting and time series. You mentioned rising computing power.
Yes.
If that continues, or if that doesn't, how do we see what we can do with more computing power, more data, and how will you think models improve?
Yes. Again, I believe the way I see it, and like, take it with a grain of salt, right? I'm no like researcher spending years and years in this, right? Again, I'm mostly a practitioner, okay? But I think the next step is really leveraging external variables. That's where that's a big challenge, okay? So multivariate forecasting is still a challenge. So even though those models that were telling you, all those advanced NLP architectures and deep learning architectures, most of them are still univariate models. Even in their like out of the box, ready to use implementations, they're univariate models. So they're predicting one series at a time. Okay. But actually leveraging, external informations to inform your prediction. I think this is where it's going to go. And, as we get better at leveraging external information to inform some kind of prediction, I think this is really what is going to unlock better performances. And again, we've seen it with TS Mixer, right? So the very recent model by Google, And that's really that was their point, right? Like they managed to leverage external variables to inform their forecasting, and that's how it managed to deliver state-of-the-art results on a lot of benchmark data sets. So yeah, I
I
think it's
mean,
where
would
it's
you say
going.
that it's kind of, you might not expect variables like not related to one domain, you're measuring I don't know, stock prices, and you don't think something's related, but like it has information and data there, so
Yeah.
can you use it? And sometimes you're just trying to find techniques and ways to make that help you improve the model.
Yeah, essentially. And also right now, we're kind of limited by what maybe we assume has an impact or has a relationship, right? Or like, the traditional way of thinking, maybe. And, when you give it to a computer, the computer has no bias, right? It's just going to check everything and see, oh, can this help me, optimize my score, right? And so maybe we are going to find out new relationships that maybe didn't even know existed, right? So
Very
yeah,
interesting.
I think that's what could happen.
Very interesting.
Yep.
Well, as a as we finish the interview here, why don't you tell me about where people can find you and
Sure.
your courses, and where people can read your work?
Yes, absolutely. So I have a blog on Medium. I'm contributing towards data science. So of course, if you're on Medium, you can follow my profile, or whenever I'm going to publish on towards data science, you'll probably see it pop out. I'm on LinkedIn as well, and like you mentioned, I do have some courses. So I have my big course on time series forecasting. So that was meant like how I would have liked to learn the subject, but I didn't get the chance. So anyway, it really takes you all from the basics to all the way to the state of the art methods, like time GPT, NBs, NHITs, everything. Like I actually show how to use those, and we're trying to touch on every scenario of forecasting, like intermittent forecasting. So when your series sometimes is at zero and sometimes at non-zero, that's like a whole entire field. So anyway, super
Yeah,
interesting
yeah.
stuff. So yeah, it's on my website. So my website is called Data Science with Marco. Um, yeah, trying to build my personal brand there,
Hmm.
and yeah, just like teach people, share my knowledge, and help anyone I can.
Yeah, awesome. Well, thanks, Marco.
Thank
Appreciate
you
it.
very much.